as an expert in observational studies of all the important parts of star formation, including the initial fragmentation of molecular clouds, the evolution of dust grains and gas chemistry, as well as the role of magnetic fields. Her group uses a broad spectrum of observational tools, including in the infrared, submillimeter, and radio bands. Sarah received her bachelor's at York University in Toronto. Then she moved to University of Victoria for her master's and PhD. Afterwards, she held her NSERC postdoctoral fellowship at the Max Planck Institute for Astronomy in Heidelberg. Then she came back to North America, holding the prestigious Hubble Fellowship at the Smithsonian Astrophysical Observatory at Harvard CFA until 2019. And we're very pleased to have her back in Canada, where she started her assistant professorship at Queen's University. So without further ado, please take it away.
Excellent, thank you so much. So I guess I will begin by sharing my screen and starting the presentation, if I can get it to go. All right, just to verify, are you able to see my cursor?
Yes.
Perfect, excellent. So that's always good to know. These Zoom meetings, you never can quite tell what is and isn't being transmitted. So thank you very much. It's very nice to be virtually at McGill and to share some of my research with you. So what I want to talk about is some work that is ongoing, both in the theoretical side and the observational side, in trying to better understand how planets form using observations of protostellar disks and protoplanetary disks. And you may notice that I do have a little helper here with me. This is Mango. He may or may not show up periodically throughout this talk. So the story today is a story of planet formation. And in very, very broad strokes, you can describe planet formation through the process of star formation. You have these stellar nurseries, these molecular clouds that are tens of parsecs in size, and through a number of steps, they form stars and planets. And so in very broad terms, this is the story of planet formation. Of course, to go from a very large cloud to a protostellar system, a planetary system, is not a trivial number of steps. There is a lot of physics that goes on. There are a lot of different elements to this particular cycle. So we can start to fill in some of these steps, because a single cloud is not going to form a single star and a single planetary system. These clouds are going to form many stars, and they're going to form many planetary systems. So the first step is these clouds end up fragmenting. They form filamentary structures. These filamentary structures fragment and they form dense cores. These dense cores will collapse under gravity and form young stars. Material will fall onto the stars, and angular momentum conservation will form a disk. And it's from that disk that we're going to end up getting the new planets. So there's a lot that goes into each of these different steps. But the story of planet formation is the story of each of these steps. And the step that I really want to focus on is what happens in the disk, the planet forming disk, and how that disk is going to produce the seeds that are going to become the new planets. And the idea here is that really the story of planet formation from that perspective is the story of how dust grains grow. Because molecular clouds, they're a combination of interstellar dust and molecular gas, and it is the dust grains themselves that are the building blocks for forming the new planets. So today I will be talking about the concept of dust grain growth, the story of dust grain growth, and how dust grains are the building blocks for planets. What exactly do I mean? Well, this is actually a complex process, because if you look at interstellar dust, it's very tiny. And if you look at planets, they're very big. So dust grain growth has to span many orders of magnitude in size. So as point of a comparison, this is an image of a cometary dust particle. It's not quite as small as interstellar dust, but it gives you an idea of how tiny these things can be. Interstellar dust grains are typically less than a micron in size. And then if you look at the Earth, radius of the Earth of order, 3,000, 4,000 kilometers, our planets are big. So you have to go many, many, many orders of magnitude larger in size in order to explain the kinds of systems that, the dust grains and how they're going to form the planetary systems that we want to see. This is a complex process. And we think that most of this grain growth is going to take place in those disks of dust and gas around young stars, the birthplaces of the planets. The reason why is that disks have the cold, dense environments that you need in order for dust grains to kind of stick together and grow bigger in size. So this is just a cartoon of what we think a disk might look like. You have a warm outer layer, and as you go into the midplane, into the middle, you have much colder temperatures because all of the material there is shielded from intense radiation coming from the young star and accretion onto the star. And that's where you can form ice mantles on the surfaces of your dust grains. And as these icy dust grains are moving around, because you have higher density and because they can stick together more easily, you end up getting coagulation, that the dust grains are going to collide, stick, and form a larger aggregate. A good analogy for this is actually something that we've seen relatively recently in Ultima Thule, which is a Kuiper Belt object that was imaged by the New Horizons spacecraft in our solar system a few years ago. Here you can see that you have an icy body and another icy body that they had somehow come together, collided, stuck together, and they're now floating around in our solar system as a much larger object than they were before. So this is exactly what we expect to be happening in the midplanes of disks, but of course on much larger scales. The midplanes of disks, the dust grains, we don't expect to be nearly this big, but the same kind of process can be applied. So there are a number of questions that are very important to understand for planet formation. How quickly do these dust grains grow? If dust grain growth is very slow, then that means it takes a lot longer for you to form your planets than if the dust grain growth processes very quickly. That means that your mass reservoir for forming planets is very different depending on this timescale of grain growth. We don't really know how the properties of disks affect grain growth or how the properties of the star or the environment of the cloud might affect the grain growth process. And so all of these are very important to understanding, again, the seeds of forming a planet, the beginning of forming a planet, the onset of planet formation. And then once you do start getting those, tiny little particles forming, the ones that are, the building blocks, how quickly do you then produce the planets, and then what sets the mass of these young planets? And really, all of these questions tie back to how big are dust grains and disks? How do we measure these sizes? And the question of measuring grain sizes has become much more prominent lately because of advancements in observational technology, particularly with ALMA. So this is a gallery of some of the observations from the D-Sharp survey that were taken with ALMA. These are real disks around protoplanetary systems. So these are pre-main sequence stars, and they all have these very complex structured disks. And what this gallery also highlights is just the variety of disk structures, disk shapes, disk sizes. So really measuring grain sizes of disks is not going to be a one size fits all. We need to take into account the fact that we are looking at a variety of systems that are going to have a variety of properties. And so that does make calculating the grain sizes much more challenging. The general approach that is taken to measure grain sizes is to take beautiful observations such as this, but to do so at multiple wavelengths. So you would observe one disk at a variety of different wavelengths. You would look at the spectral line distribution, so the flux as a function of wavelength. You would construct a model to describe how the flux should change as a function of wavelength that is then dependent on your grain properties. So the idea is that if you have large dust grains, they are much more efficient at emitting at long wavelengths than small dust grains. So you can use the shape of your spectral energy distribution to constrain what kind of dust grains you should have in your disk. And if you do that, you can infer the grain size distribution in your disk. And so this is something that Carlos Carrasco-Gonzalez did for the HL tau disk. This is a plot that shows your maximum grain size in the disk as a function of radius. The purple curve is what they got from SED fitting, so just taking the flux at a bunch of different wavelengths and fitting a model to that. And then the dashed curve is a power law distribution that more or less follows the general shape that you see for the grain sizes from the SED fitting. So the interesting thing here is that you'll notice it's not smooth, that there are all these bumps and wiggles. And if you've ever seen a beautiful ALMA image of HL tau, you've probably seen this one. HL tau is not a uniform disk. It has gaps, it has rings, and you can see variations in the grain size distribution that correspond very closely to those gaps and to those rings. So it suggests that we do have a correspondence between where we see the structure and where we're going to see enhancements of grain growth and the likely locations of where future planets could potentially form. So this is, the broad approach that we take in order to understand and to measure grain sizes. Of course, this is not the end of the story. Reality is never as clean and simple as we would like it to be. And there are a number of challenges that still remain in understanding grain sizes when doing this SED fitting approach. In particular, there are a lot of unknown properties regarding dust, and they are going to affect the reliability of your model and the precision of your model. We don't know the sizes and shapes and the structures of dust. Shape, are they spherical? Are they elongated? Are they irregular? Structure, are they compact? Are they porous? Optical depth is a problem. If you're optically thick, you need to do corrections for the missing flux that you're not seeing because you're only looking at a surface layer. Dust can come in a number of different compositions. Is it silicate dust? Is it carbonaceous dust? That could affect some of your properties. The dust temperature in disks is very complicated because you have a temperature gradient along the line of sight. And if you don't take into account that variation in temperature, you could misinterpret your SED fitting. And if you have high optical depth, you could have also dust scattered. And if you have scattering, that can affect your ratio of the fluxes at different wavelengths because some wavelengths will scatter more than others. And ultimately, what I want to take away from this is, yes, dust is complicated. We do have to make a number of assumptions, and changing some of these assumptions will affect your grain sizes that you get out. And that will also affect then your timescales for planet formation. So there are a lot of challenges in using dust, and having only one technique to infer grain sizes makes it really challenging to try and capture grain growth as a function of evolutionary stage in disks, because these parameters are going to be changing for every disk and for a function of time. What we really need to start doing is developing more methods, independent methods that can constrain dust grain sizes, so that we have multiple approaches to try to get to the same answer and therefore have a better understanding of how grain growth works. And hopefully by the end of this talk, I will have convinced you that polarization from dust cell scattering is a wonderful tool that we can use to be an alternative method to measuring grain sizes in disks. And this will allow us to better understand grain growth and to constrain the sizes of dust grains at early stages. So the principal mechanism here is that if you have unpolarized light, and that unpolarized light hits a dust grain, a molecule of some kind, that scattering signature that you get can be polarized depending on the angle at which it is scattered at. This is just Rayleigh scattering. There's nothing too complicated about this. It just says that if you are scattered at a very steep angle, you will be polarized versus shallow angle, you are not. The idea for disks, however, is that the scattering is not coming from the star, which might be most people's first guess. And the reason is that at the wavelengths at which we measure these disks, which is sub-millimeter or millimeter wavelengths, the star does not matter. It is not nearly as luminous as the emission coming from the disk itself. And so what ends up happening is instead of having scattering coming from the star, we have what's called self-scattering. That is a scattering of light from a photon that, from a dust grain that hits another dust grain. So in this little cartoon, you have a dust grain located right here. It's emitting light that is completely unpolarized. It's just emitting light. That light hits a neighboring dust grain and could scatter. And depending on the orientation of how that system is constructed, you can get that scattering light signature to be polarized. What you need to have is an anisotropic radiation field. That is, you need to have a preferred direction for the radiation to hit this particular dust grain in order to have a polarized signature. If you have a dust grain that is in an isotropic radiation field, then you have scattering events happening at all directions equally. And so all of the scattering events are going to have, in the sense, the same, an unpolarized net gain. But if you have an anisotropic radiation field, there is a preferred direction that this radiation is hitting that particular dust grain, and therefore, depending on the angle at which things are being scattered to reach us, there will be a preferred direction for the polarization. So in the case of a dust grain that's at the edge of the disk, the preferred direction is coming from the interior. So we have this polarization signature that we would expect right here. And if we apply this cartoon to the rest of the disk, we can say that we can estimate what the morphology of the polarization from self-scattering will be just based on the anisotropic radiation field. So if we know how the radiation field can be expressed, we can predict the polarization signature from self-scattering. And so for this particular geometry, this is what we expect. One moment. If we change our geometry of our disk, such as we go from a face-on disk to an inclined disk, then suddenly our polarization signature from self-scattering changes quite drastically. And again, it has everything to do with the radiation field anisotropy and also the direction of the scattering signature. And these are entirely predicted just based on geometry and your description of the radiation field. So these cartoons illustrate the predictive power of dust self-scattering. And that means that if you have a good model for your disk, you can predict very nicely what you should see from self-scattering in terms of the polarization signature. And you can argue that H-L tau is probably the disk that we have the best understanding of, just because it's been so well observed with such high resolution and so many wavelengths. So as an example, this is a model of H-L tau. You've got the brightness temperature here, you've got optical depth here, you've got column density of dust, and you have the spectral index, which is just the slope between different wavelengths from different observations of this particular disk. So we have a fairly good understanding of the emission structure of H-L tau. If you take a model such as this and you run it through an expectation for self-scattering, because you know where the structure is, you know where the dust is, you know roughly how the temperature is changing as a function of radius, then you can predict what the polarization signature for H-L tau should be from scattered light. And this is something that Akimasa Kataoka did for H-L tau. This is a prediction of the polarization from self-scattering for this disk at 870 microns. And in a few slides, I'll show you what the observed data look like. But for now, this is a prediction. This is what we think we can get. So that tells us how we can predict self-scattering. The next question is, how does that help us with grain size? And the important thing here is that to get a polarization signature from self-scattering, you don't just need to know what kind of radiation field you have and where your dust is. It also depends very strongly on whether or not you have large enough dust grains to produce that signature. So this is a plot that shows the probability of a scattering event at 870 microns. So for you to observe a scattering event at 870 microns as a function of your largest grain size. And in general, your scattering signature is most probable if you have large dust grains that are about the same order of magnitude in size as the wavelength of light that you're looking at. So that's what you see here. And then as you go to much smaller and smaller dust grains, compared to the wavelength of light, you have that fall off from Rayleigh scattering. So this is what we would get for just the scattering part. But we're not just looking at scattered light, we're looking at scattered polarized light. And the probability of that scattered light being polarized is dependent on the grain size, but in the other direction. You are actually more likely to have a polarized signature if your grain size are on the small side than if they're too big. And so you end up with a crossing of two different kinds of probabilities. So if we were to combine these two effects, what we end up getting is the probability of having both polarized, scattered light for a particular distribution of grain size. And what this represents is kind of a narrow window of grain sizes that are optimized to produce this signature. So if you detect this signature, this tells you information about what kind of dust grain sizes you have. And this is for 870 microns. You can imagine that if you were to perform this kind of exercise at different wavelengths instead of just 870 microns, you would get slightly different windows of where you're going to most likely detect polarized self-scattered light. And so that's what we have here, is that multi-wavelength data can give you different insights into different grain size distributions. So for example, this purple curve shows what 7 millimeter observations would be versus this red curve, which is 340 micron wavelength observations. The 7 millimeter wavelength observations are much more sensitive to large dust grains than what we would see at 340 microns. And so by looking at multi-wavelength data, we can start to piece out what kind of grain sizes we have in these disks, because the signature is so dependent on that property. There is one caveat to keep in mind, and that is the other factors that affect us, like composition, the shape, the compactness of the dust grains. These things are going to still affect the shapes of these curves. So I want to caution that the theoretical framework of using self-scattering to directly correspond to a grain size is still under development. This is not something that is fully figured out. But I would also like to highlight that this is a new field. We hadn't really considered polarization and self-scattered light at sub-millimeter wavelengths until about 5 years ago. So this is a growing and new field, and it is still something that we are fully trying to understand. But my hope is that I've at least convinced you that this process at a bare minimum does require the presence of large dust grains, or at least dust grains that are considerably larger than what you would see in the interstellar medium. And that means that you can use this as an independent probe of where we are seeing evidence of dust grain growth and where we are not. And that is something that we can easily utilize in understanding the timescales of grain growth while we are still developing the theory itself. So just as a quick summary of what I've talked about so far, I mean, the goal here is to look at the onset of planet formation, and to form planets, you need to grow your dust grains. They can't be, some micron sizes forever. They have to form pebbles, they have to form boulders. And the time scale for that is not something that's well understood, because it's really challenging. There are a lot of unknowns about dust grains. And the hope is that we can use multiple mechanisms to tackle this problem from different directions so that we can better understand grain sizes and disks at different evolutionary stages and in different environments and under different circumstances. So this is where dust self-scattering can be a really important tool to better infer grain sizes. So for the remainder of the talk, I want to tackle 3 particular problems, and this is going to now be a flip from talking more about the theory and what we expect to see to now, what are we actually seeing? Is there evidence that this signature is present in disks? Is it a common process or is it rare? And what can we say about the timescales of grain growth based on what we've seen so far? So to begin with, is this process even detected in disks? Yes or no? And I think it's important to highlight that this question could not really be asked until recently because of facilities like ALMA that are allowing us to detect polarization in disks with, high resolution, high sensitivity, to do things that we've never been able to do before. To give you an idea of how much the field has changed, here are observations of polarization in 3 disks that were taken before the era of ALMA. So these are disks that can be observed with CARMA, with VLA, SMA, and the observations are fairly sparse. In some cases, you can have multiple beam detections, but for the most part, you don't. It's not well-resolved polarization observations. And this makes determining the origin of the polarization and the structure of the polarization much more challenging. I will note that the polarization vectors that you see in these plots have all been rotated to 90 degrees, because at the time that these papers came out, the understanding of polarization was it's all from magnetic fields. And the polarization signature you see from dust emission is 90 degrees rotated from the magnetic field direction. So these were all rotated by 90 degrees. Everyone thought it was magnetic fields, and that was the end of the story. Now in the era of ALMA, we are able to spatially resolve the polarization, and we're also able to capture other polarization mechanisms. And I will get to alternative mechanisms very shortly. But for now, let's look at these same 3 disks. So we've got HL tau here, we've got DG tau here, and we've got L1527 here. The same 3 disks, but now the polarization is what we get with ALMA. And the difference is quite striking in the terms of the number of vectors that we see, the fact that we are spatially resolving the polarization over multiple beams. The resolution element is shown in the corner of each of these plots. So here we again have HL tau, DG tau, L1527, 3 disks, 3 different evolutionary stages, and the polarization is well resolved with ALMA in all 3. The polarization of all 3 of these disks are also completely consistent with what you would expect from self-scattering using the simple models that had been described earlier. So as a point of comparison, this is the predicted 870 micron polarization from self-scattering map of HL tau by Akimasa Kataoka. And this is the observed 870 micron polarization of HL tau from ALMA. This came first. The model was published before the observations. So it's interesting how closely the observations match the polarization from self-scattering, and the fact that the prior expectation that all polarization in disks was tracing magnetic fields ended up being wrong. At least in these 3 disks, it looks like we're quite possibly just tracing the self-scattering process. And it isn't just these 3 disks. Lots of disks show this signature. On the top here, you have 3 protoplanetary disks, and on the bottom here, you have 3 protostellar disks. All of them have polarization signatures that are consistent with self-scattering based on how we expect the radiation anisotropy of these disks to be described and the structure of these disks. So they are all consistent with dust self-scattering, and therefore they're not tracing magnetic fields in the end, which is a loss for people interested in magnetic fields, but it can still be a gain for other science. So there is definitely evidence for this process being present. The next question is, how common is this process? Is it rare, or have we just selected the ideal disks for detecting it, or is it something that is actually quite substantial and very, very common? So one thing that needs to be addressed is that it isn't just polarization from self-scattering that can be present in disks. I've mentioned magnetic fields as being a mechanism, but there are also other mechanisms that can be present in disks that have been identified in recent years as potentially being a huge factor. And it's not something, again, that we had thought about prior to 5 years ago. It's only something that's really come about in the literature and in theory and slowly in observations today. So let's come back to HL tau. This is the 870 micron map of HL tau. And disks like HL tau are well observed at this wavelength, but we can also observe this disk in polarization at other wavelengths. And some disks, like this one, show a change in the morphology as a function of wavelength. So here's, again, HL tau at 870 microns. Here's HL tau at 1.3 millimeters, and here's HL tau at 3 millimeters. Same disk, 3 different wavelengths, 3 different morphologies to the polarization. This is difficult to explain with one mechanism, and ultimately what the solution that has been put forward is that there are more than one polarization mechanisms that are affecting the observations. In the case of the 870 micron data, you are looking most likely at self-scattering because this is where the emission is most optically thick, and you need to have optically thick emission to have scattering to be significant. So that would make sense. But as you go to the band 3 data, which is 3 millimeters, your emission is less optically thick. And so now you're starting to see less likely scattering events. And so other mechanisms are probably coming out. And there are now multiple mechanisms that have been proposed for disks. Magnetic fields is one, magnetized torques is another, getting grain alignment from torques from a radiation field, aerodynamic alignment or gold alignment, which has to do with the gas motions in the disk. The list is growing rather than shrinking, and there might be even more in the next few years. So this has made a number of challenges because many of these factors don't matter on large scales, but they do in disks because they depend on large grain sizes and they depend on having high densities of dust and or gas. So these are going to complicate our understanding of dust self-scattering as a probe for grain size growth in disks. So if we want to determine if self-scattering is common, we need to really make sure that we are tracing it. And part of the problem with making sure that we are absolutely tracing it is that we don't really have a large sample size just yet. This is still relatively new. We are growing our sample sizes, but for the most part, we have small numbers that are piecemealed all over the sky in different star-forming regions. And most people are targeting the biggest and brightest things because those are the most likely ones to have a detection. So we could have biased samples. If you're looking at the biggest and brightest, and those tend to be where the self-scattering is located, then that would affect your understanding of how common this process is. So what we really need to do is look at large surveys and unbiased samples, and also start probing multi-wavelength data. And so with that, I would like to advertise a survey that I led in Ophiuchus with ALMA. This is a unbiased, high-resolution polarization survey of all of the embedded protostars in this cloud. So it's the largest sample to date of polarization, looking at 26 different systems, all in one star-forming region. And the data are all publicly available. So I've released the data products. You're welcome to use them and to have fun with them as much as you would like. So there were 26 systems that were targeted, and of those 26 systems, 37 young stellar objects were detected, and that would signal lots of good statistics, which would be great. Unfortunately, about a third of them were actually detected in polarization. So the majority of the sample were not detected in polarization. Part of that is because the sources were faint, and so we didn't have enough sensitivity in order to say anything about the polarization. But other ones were bright, and there are probably other reasons why we didn't detect anything, which I will get to very shortly. But what I want to focus on at first are the objects that were detected in polarization. So this is a gallery of the 14 young stellar objects that were detected in polarization. And they have some variety of structure. There are a couple of them that show extended structure, but most of them show relatively uniform polarization, which is hopefully familiar to you if you remember the little cartoons that we had before. So if we wanted to understand how common polarization from self-scattering is from the sample of 14 of objects that we have so far, we need to infer what kind of polarization mechanism could have produced this kind of information. And that is challenging to do because we only have one wavelength of data for most of these objects. And as I've alluded to, you can have multiple polarization mechanisms that can produce different signatures, and that signature can change as a function of wavelength. So ideally, we're going to need to make some assumptions and follow up targets with future data to verify these assumptions. So with the current data in hand, what we did was a morphological assessment of the systems. We looked at the morphology of the polarization, the geometry of the disk, and the opacity of the dust. The idea being that if all three of those were favorable to self-scattering, then we have a system that is consistent with self-scattering. And if they are not favorable to self-scattering, then we have a more complicated system that requires additional follow-up. And based on that very broad morphological assessment, we did find that the majority of the young stellar objects in the sample were consistent with self-scattering. So 10 out of the 14 systems, we could say, are at least entirely or partially consistent with self-scattering. That means that this process, at least in our sample at 1.3 millimeters with ALMA, is the most common mechanism for the polarization signatures seen in disks. And that's a substantial statement to be able to say that this is a common mechanism. We can use this in observations of disks to look at grain growth. So here's just some of the examples of the polarization that we see. And again, this is the cartoon of what you would expect to see if you had a highly inclined disk. And indeed, in cases where we have highly inclined disks, we see uniform polarization aligned with the minor axis, exactly what we would expect given this cartoon. All right, so I guess the next question is, which of these disks are showing signatures of polarization from self-scattering? It's not all of them. Why are some of them not detected? And the ones that are detected, probably unsurprising, are the ones that are higher mass. We generally do see polarization from self-scattering towards the disks that have higher mass. And unsurprising, because if higher mass corresponds to higher surface density and higher surface density corresponds to high optical depth and larger grain sizes, you would expect self-scattering to be favorable because you need both high optical depth and large dust grains in order to see that signature. So this doesn't seem to be anything outside of what you would expect given our understanding of how this process is proceeding. But another thing that we did find is that disk inclination is also very important to detecting this signature. So just as a point of comparison, this is WL17. It is the brightest source in our sample that was not detected in polarization at all. Our 3 sigma upper limit to the non-detection is 0.3%, which is in the instrument noise. So this is a very bright source and a very massive disk that has no detected polarization. It's also a system that has a relatively low inclination. Inclination angle of it is about 30 degrees. It's not entirely face-on, but it's got a relatively low inclination. For a relatively low inclination, you would expect to have some symmetry in the scattering signature that you would see. So this is the cartoon that we looked at before. This is the expected polarization morphology if you had a completely face-on disk. And if you have a disk that is small and not super large compared to your beam, and you plop a beam on this region, you're going to have some symmetry within the polarization signature that's going to end up canceling out. So it's going to depolarize. And that means that it's very challenging to detect a polarization signature if you don't have very fine resolution that can separate the polarization signature at each of these different points. And this disk is resolved, but it's not resolved over multiple beams along each of the axes. And so as a result, the polarization morphology, if it looks kind of like this, might actually be unresolved in this particular source. As a point of comparison, this is GSS 30 IRS1. It's smaller than WL17. Its estimated mass is about 5 times smaller as well. So it's a smaller disk in size, a smaller disk in mass, but it is very well detected in polarization. This is a highly inclined disk. Its estimated inclination is 75 degrees, and the polarization morphology is uniform and aligned with the minor axis, exactly what you would expect from self-scattering. Again, here's that little cartoon to illustrate the similarity. For this particular disk, if you have uniform polarization, you will still detect that polarization even if it isn't well resolved, because you have no cancellation within the beam. You have a uniform orientation within your resolution element. So what this suggests is that, disk mass is important and brightness is important, but inclination is also very, very important given your resolution. If you are interested in grain growth, you are more likely to detect self-scattering in highly inclined systems by virtue of the simplicity of the polarization morphology compared to more face-on systems. And so depending on the type of object that you are trying to target in future observations, you need to take into account, not just the detectability in terms of how bright your source is, but your detectability in terms of how well you can resolve it. So this is just to summarize, the question of, how common this is. It's common at 1.3 millimeters, but it is more likely to be detectable if you have a high mass disk, a high inclination disk, and a disk that is well resolved if it is at low inclination. So there are challenges that are different depending on your target. So something to keep in mind if you are interested in future ALMA observations. All right, I know that I am slowly running out of time, so I will try to cover this very last question about how we can sort of use self-scattering to infer different properties about timescales of grain growth in disks so far. Again, the theoretical framework is under development. We are still working on this. So I'm going to use detections of self-scattering as a proxy for grain growth, not as a direct tracer of what grain sizes are present. And I'm also going to, again, caution you that a non-detection of self-scattering does not necessarily mean your grain sizes are small. It could just mean you have unresolved polarization structure, or you're detecting polarization from a different mechanism. So it's something to keep in mind that I'm only detections as an indicator of grain growth and not focus on the non-detections as being, oh, these systems do not have large dust grains. The other thing I'd like to point out is I'm just going to focus on very young disks, so the class 0 systems, the earliest stages of star formation, within the first few tenths of a megayear in the formation process, just to see whether or not you can form large dust grains quickly. Because if you look at simulations of dust grain growth, what they generally show is that you get millimeter-sized dust grains, which is about at this point right here, very early in the process. This is at 10 to the 5 years, 10 to the 6 years. If you are at a point that's, let's say, 1 AU or even 10 AU within a disk, but out to 100 AU, you don't get such large dust grains, and particularly you don't generally form them at all. And that means that grain growth is potentially very much limited to the inner radii of these disks. And so the question is that something that we are seeing in observations? So let's look at some of the class 0 systems that have been observed and have been observed to have polarization consistent with self-scattering. We've got VLA 1623A and B, we've got HH212, and we've got L1527. These are observations either at 1.3 millimeter or 870 micron. And what these observations indicate is if we are seeing self-scattering, then you've got 100 micron size dust grains present in these disks out to 40, 50 AU. And this is happening at, again, less than 0.2 of a megayear in time. And that result is not unreasonable given these grain growth models. So this seems to match expectations from grain growth models. But if we want to look for larger dust grains, we're going to need to look at self-scattering at longer wavelengths. I showed this image earlier. Remember, if you want to look for millimeter-sized dust grains, you are most sensitive to seeing that at 7 millimeter scattering signatures, because the scattering signature is a strong function of the grain size. So you've got that window where you would expect the grain size distribution to be favorable to the scattering signature. at the wavelength that you're looking at. So at 870 microns, you're not likely going to trace the signature at all from 1 millimeter size dust, whereas at longer wavelengths you can. And at present, the only facility that can do that is the VLA. And there are a couple of young disks, class 0 disks, that have polarization detections from the VLA. You've got IRAS 16293 and you've got IRAS 4A. The mechanism behind the polarization is a little bit under debate. There have been some indications that it could be consistent with self-scattering, but maybe not entirely consistent. So there could be multiple mechanisms present. But if we are seeing evidence of self-scattering, then we are seeing millimeter-sized dust out to 50 or even 100 AU on such small timescales. And that would be inconsistent with what we would expect from these grain growth models. So this would be indicative of that at least these two disks are rapidly forming very large dust grains. But at the moment, we are very much limited in the capabilities of going beyond these two types of disks because they are exceptionally bright. And so this is something that future work, if we can get ALMA band 1 or NGVLA, that can really be a game changer in looking for very large dust grains from this process. All right, so I guess there's one other thing that I would like to mention is just how accurately are we doing this? Are we getting the right grain sizes? And one thing that I would be amiss if I didn't acknowledge is that we are seeing inconsistencies between the grain sizes that we get from continuum modeling. This is the original approach that people have used to look at grain sizes in disks, and self-scattering. So this again is the model of grain sizes in HL tau by Carrasco Gonzalez. This was taken using continuum modeling of multiple wavelengths. And from this model, they got maximum grain sizes of 1 millimeter. Fantastic. If you look at self-scattering of HL tau, same disk, but you acknowledge the fact that you do not detect self-scattering at 3 millimeters, you would infer a maximum grain size of 100 microns, an order of magnitude less than what you get from the continuum modeling. So there is a discrepancy here, and this is a discrepancy that has not yet been resolved. We are still trying to understand the theoretical framework of self-scattering, but at the same time, we may need to revisit how we do continuum modeling and making sure that we have all the physics in there that we need to, because ultimately these two mechanisms need to agree. We're looking at the same disk, we're looking at photons of light coming from the same disk. We need to be able to resolve this discrepancy. So this is still an open problem, and one that really does still need to be understood. But for now, what I would like to do is actually end, not with conclusions, but what I like to think of as takeaway thoughts, things that I hope you exit this talk with. First, I want to make it very clear that self-scattering does have a lot of benefits, even though we're still developing it. It adds extra dimensions to modeling because you're fitting the continuum distribution as well as the polarization. And so that combined should give us more constraints, provided that we are putting in accurate assessments of the data going in. Based on the survey data that I've got for Ophiuchus, we are seeing that self-scattering is common in disks, particularly young disks. It does seem to favor disks that have higher masses and steeper inclinations. So depending on the system that you want to observe in the future, you need to take those caveats into account when determining what kind of observations you need. I would also argue that if you do not detect self-scattering in a disk, that does not mean you have small dust grains. You could still have large dust grains. It could just mean that you have other conditions that are not favorable to your detection, like you may have unresolved polarization structure that needs to have higher resolution data to be better understood. And that's something that I think we need to take into account more, is that a non-detection is not an indication of small dust. It's just an indication that your polarization structure might be a little bit more complicated than what your observations are able to detect. We do also still have this open problem of a disagreement between the continuum modeling and the self-scattering. And that's something that we need to resolve, especially if we're trying to infer how large grains are. We're just starting to scratch the surface of how big grains can be from self-scattering, particularly if you start including VLA data. So if we want to really understand, grain growth and put a size and a limit and a location to where large grains are, we need to do a better job with this. And I'm very hopeful we will do a better job. Again, I'd like to point out that this is a growing and relatively new approach to measuring grain sizes in disks, and we've done a lot in only 5 years. So I really do look forward to utilizing both observations and theory to have at it and really have a good, strong understanding of grain sizes and grain growth in disks, and to use these tools to look at the onset of planet formation and where and when we start to see those seeds first popping up in disks. So with that, I'm happy to take questions, and I thank you for listening.
I think Jordan's away, so thank you, Sarah. Let me clap for everyone else.
Thank you, and apologies again for Kat running around in the background. Working from home.
Yeah, not a problem. We all understand. So let me start off with question. I actually have two questions, but I'll just ask one. I just wanted to get your thoughts on, because the impression that I had from reading some experimental papers on colliding the dust together, like my impression is that like it's actually really difficult for the dust grains to stick. So I was just wondering, like, your thoughts on, because you did mention that from your results, like it is possible to have pretty rapid growth in certain systems. So I was just like wondering, like, how do you mesh those two together?
Yeah, so dust grain coagulation, there is an efficiency to it. You can also destroy dust grains if you hit things too rapidly together. And so you can, it's called sputtering when you instead of growing them, you break them apart. So as you get, if your grain ends up being too irregular in shape and too porous, it's very easy to break it rather than to grow it. There are laboratory experiments that have demonstrated that you can start growing dust grains, but it's very challenging to put those laboratory experiments in the context of astrophysical conditions. It's very difficult to match those specifically. There's been a lot more work, I would say, on the numerical modeling and developing grain growth through that. And primarily, you have to assume an efficiency factor in that sense. And if you have high enough densities, you will eventually start building up larger and larger dust grains. But it does take a non-trivial amount of time. But it does seem like you do need to, it can't be too long. Otherwise, we can't explain the fact that we do see disks at centimeter wavelengths. So the very fact that we even just detect these systems at millimeter or centimeter wavelengths does indicate you likely have relatively large dust grains present, because those dust grains are the ones that are most efficiently going to just emit radiation at these long wavelengths. A 1 micron size dust grain is not going to emit efficiently at 8 millimeters. You do need to have larger and larger particles just to explain the radiation being present, not even ignoring the centimeter, ignoring the polarization. You do need to have large dust grains just by virtue of having the radiation present. So that does mean that we are expecting grains to be, even in these very young systems, which are, class 0 stage, there has to be some grain growth. Now, there can be some grain growth even before you reach the disk. You could have some grain growth in the envelopes around young stars, and then that material gets fed into the disks. So the grain size that you even just start with may not be accurate. We might actually be starting with grain sizes that are approaching the millimeter, centimeter sizes even before you get to the disk. It's just we don't tend to see envelopes as strongly as we do disks, and so it's hard to determine how large grains are in that sense. I'm not sure if I answered your question sufficiently. I think experimentally it's hard to match the astrophysical conditions, and even if you do numerical modeling, you still have to assume some sort of efficiency factor. But in the end, we do know that there has to be grains that are of decent size, even in early stages. Otherwise, we wouldn't detect these systems at all.
Okay, thanks. Jordan?
I'll ask a kind of big picture protoplanetary disk question that may or may not be relevant here. But I'm curious about the extent to which we expect protoplanetary disks to have any memory of the properties of the GMC they form in. So in this context, particularly metallicity, would like order of magnitude or factor a few changes in the metal content of the parent cloud have any discernible impact on the formation of dust in a protoplanetary disk?
That is an excellent question. I haven't given it too much thought, to be perfectly honest. I would assume that there is going to be some degree of dependency, because depending on the metallicity or even just the composition of your parent cloud, that will change the kinds of dust grains you have, but also will change the composition of the ices that form on the dust grains. And that will affect a number of different processes. So that can affect your gas chemistry, and your gas chemistry can affect how materials stick onto dust grains. So carbonaceous dust is more likely to have carbon-rich ices on them, and versus silicate dust, and so that can change the composition there. If you have so silicate dust responds differently to magnetic fields, so that can change other aspects of the star formation process. Carbon dust and silicate dust have slightly different opacities, and they have potentially slightly different scattering efficiencies. So, if you have bare grains, that will have a difference. If you have ices, that will have a difference. So there are ways that the metallicity, but I would say also the composition of your cloud could affect how your observations turn out, but also how the grains are going to grow as a function of time. But I don't know specific examples of where that's actually been tested. And so I can only give you a broad strokes, this is how it could have an impact, but not, this is specifically how somebody has tested that impact. It's very difficult just to form a disk, but to translate all the information from that 10 parsec scale cloud to a 100 AU disk is quite a substantial also change in scale.
Okay, that's perfect. That's exactly what I was looking for. Thanks.
Bryce?
Yeah, thanks for the interesting talk. I have a couple of extremely basic questions, so I should probably be obligated to say that I'm very far from this area of research. But
that's quite all right.
If I think to like even our own galaxy, our own solar system with the Kuiper belt, for example, anything that we see is usually a reflection of light coming from the sun. But you mentioned that in order to detect these polarizations, the light that you're seeing is not light that's coming from the central star. It's light that's being radiated by the dust. But my first basic question is, why is this dust radiating anything in the first place? I mean,
nope, that's an excellent question. So the dust grains have a non-zero temperature. And so they are going to emit just by virtue of having a temperature. You could think of it as a black body, but they are a modified black body because dust grains are not good emitters. They're very bad at these wavelengths generally. And so we call them modified black bodies because there's an efficiency factor to their emission. And the larger the dust grain is, the more efficient it is at emitting at some millimeter wavelengths, but that's really the variance there. So, dust grains might be 10, 15 Kelvin, and so they are primarily going to peak at far infrared sub-millimeter wavelengths just by virtue of that temperature.
I see. Okay, that makes perfect sense. And the other thing was the plot that you had, which had the likelihoods of both the self-scattering and the polarization. They were kind of inversely related, right?
Yes.
That is actually really confusing to me as well, because I guess you also mentioned that the polarization comes as a virtue of the fact that you have self-scattering. So if you don't have self-scattering, why is this likelihood of detecting polarization?
Yes, yeah. So it's basically the likelihood of a scattered event being polarized. So the idea is the likelihood of scattering is very low, but if there is a scattering event, oh man, it's 100% likely to be polarized.
Okay. So then that's why it makes perfect sense to kind of sum these two in terms of looking for your peak probabilities. Okay.
So sorry, 1 second. There we go. Please continue.
Yeah, no, it's a good explanation. I was just saying that I guess that is why it makes sense to sum these two, is your total likelihood of detecting anything is right in this region where they cross. Yes.
So if your grains are too big, you're going to get a scattering event, but that scattering event will not be polarized. Whereas if they're too small, you're unlikely to have a scattering event, but if you do, it will be polarized.
Okay, thank you.
You're very welcome.
Pierre.
Hi, Sarah.
Hi, Pierre. How are you?
Yeah, I'm fine.
Good.
Very good talk. A lot of progress was done during the last 5 years. So that's very, very encouraging. There are similarities with what is happening in the optical and near infrared. When the optical depth increases, you go from single scattering to multiple scattering. Do you see something similar to that in the submillimeter and millimeter?
Yeah, so for the most part, we do, I believe everyone assumes geometrically, for the most of the theory side, you assume geometrically thin disks, and so you're likely looking at a single scattering event. There are studies that are now showing that optical depth does, like if you have a geometrically thick disk, that does affect the polarization signature that you see, and you probably can get more scattering events in those regards. And what happens if you have a polarization signature from your emission also impacting then a scattering event? Like if you have an elongated dust grain that emits polarized light, well, what happens if that polarized light then hits a neighboring dust grain? How does that polarization in the intrinsic polarization affect the scattered polarization? So this field, as I say, is definitely growing and looking at many different avenues that we can add additional complexity to the overall theoretical framework. And I don't think we have a full-on solution. Part of the problem is a lot of these things you look at for a single dust grain rather than a distribution of dust grains. And that does make it a lot more challenging to say, okay, this is what happens for a single dust grain, but now you're going to put it in a distribution and see what would happen if you had, a disk's worth. That hasn't been done yet for a number of these questions, I think. So I think the short answer to your question is this is being worked on, but I don't think it's been fully realized just yet.
A lot of work still to be done.
A lot of work, but a lot of work so far. I mean, it's amazing how we've gone from 5 years ago, all polarization is magnetic fields in disks, to polarization can be, 5 or 6 different things, and we need to understand all 5 and 6 of those different things.
Thank you.
And we'll take one more question from Mohit.
Hey, Sarah, nice talk. So I have a question that is, I think, more broad in the sense that I'm wondering if we can use these sub-millimeter dust particle observations to say something about whether gravitational fragmentation or co-accretion models of planetesimal formation, which one is like more suited. So my question is related to this. I think there is a bouncing barrier that especially associated with silicates at, if I'm not wrong, decimeter size, I think grain size. So I'm just wondering whether we can use these scattering results to study and see where these, where I think this is whether just using this core accretion model, whether we can see this kind of issues, especially near to the core of the accretion disk.
So I would say for these particular observations, you would not be able to, because we don't have high enough spatial resolution to see that kind of nuances within the disk. If we come back to this, for example, image of HL tau that I had showed much earlier, if I can find it, here it is. If you wanted to see variation in grain size in these sorts of structures, but with polarization, you need to have exceptionally high resolution polarization measurements of a disk. And for the most part, because polarization is still quite challenging, even with ALMA, to detect, we've not really done such high resolution measurements. There are projects to start doing that with ALMA, but they have not received their data or full data as of yet. And so in the future, I would like to think, yes, if you could get very high resolution data that you could measure polarization in each of these different rings, and you could resolve the polarization in these rings, you could potentially start looking at variation in grain size as a function of radius within the structures of a disk. There are probably only a few disks that are close enough for us to realistically do that. But if you could do multi-wavelength data with something like that, and you had yourself a disk model that you could incorporate things like decimeter size dust into, you would be able to test for that. And I think that is something that could potentially be done in the future, but the current polarization data of scattering just do not have the resolution to see gaps, much less detect such fine things, or even to detect variations in grain sizes between rings and gaps. But there are observations that, for example, have seen polarization variations between a dust trap and the rest of a disk, where you can see that the polarization does show a variation where we would expect the grain sizes to be larger than the rest of the disk. And so that could be a case where you could, use that information to start building those models. But where you are interested in looking, we do not have the current capability of detecting that with observations, but hopefully soon.
So related question. I'm so sorry. I think it's supposed to be the last question, but so at what frequency you think these kind of observation can be optimally done, especially if you want to study the decimetric emission?
I mean, I don't even know if, the observations I've described will definitely be able to do it, but they are the most likely ones that would. As I said, I do know of projects that are accepted with the current shutdown of the array. I don't know when they're going to be observed. I could not predict it. I do know they do require a fair amount of time, so it may require more than one cycle to get all the data. But I'm hopeful that they will. If you want to talk more about that, I'm happy to talk more about that, afterwards.
Thank you very much.
Okay, with that, let's thank Sarah again for a wonderful talk. And again, I'll just clap for everyone. Okay, and that's the end of the seminar and the last seminar of the semester. Have good holidays, everyone.